All right, we've covered point estimates now in the previous section, so now let's talk about uncertainty. So because these point estimates are generated from samples rather than from the entire population, there's some uncertainty associated with them. So we know that in our sample, the green folks are taller than the blue, but there's some uncertainty involved. We're going to be talking about three different measures: standard deviation, standard error, and confidence intervals. Let's start with standard deviation. So standard deviation is a measure of how spread out the heights in our samples are. So we know that the average height here is 68 inches, but that doesn't necessarily mean that every individual in our sample is 68 inches tall. So standard deviation tells us how spread out those heights are. So let's start by examining a visual representation of standard deviation. So here I've plotted the heights with each dot corresponding to an individual in our sample. So if you see along that bottom axis or the x-axis, I have heights, so it varies up to 72.5. And I can draw a line right here at that mean, 68 inches. And looking at these dots, this falls about where we would expect it to. And so this black dashed line here represents the mean plus 1 standard deviation. And again, it's a way to understand how spread out the points are from the mean. And I can also draw a dashed line to represent the mean minus 1 standard deviation. So if the heights in this sample were closer together, that is, if they were all closer to 68 inches, the mean, then these lines would be closer together. In other words, the standard deviation would be smaller because there'd be less spread. Okay, so the actual calculation of standard deviation is achieved by subtracting the average height, so in this case, 68 inches, from each of the measured heights for each participant in the sample. And then we add up these differences, and we take the square of that summation, and then we divide that by the total number in the sample. So in this case, I had 18 people, so I'm going to divide it by 18, and then take the square root of the whole quantity. Okay, so that's a standard error. So I take all those heights individually, I subtract the mean from them, I take the square of that summation, I divide by the sample size, and then I take the square root of that whole quantity, and that'll give me this measure of spread, standard deviation. The standard error is then calculated by dividing the standard deviation by the square root of the sample size. So the standard error is basically the measure of variability for our point estimate, the mean. And so in this case, I'm going to be dividing it by the square root of 18. So notice that this calculation is dependent on sample size. So the size of your sample plays a role in the standard error. As your sample size increases, your uncertainty decreases. And this makes sense because from the equation that we just walked through, since we're dividing by the square root of the sample size, as that sample size increases, that number the overall number is gonna decrease. And this also kind of makes some logical sense if we think about it. So if we've captured more of the target population, then we're likely to be less uncertain about our result. And so as that sample size is bigger, we're capturing more of the target population, and therefore our uncertainty is going down, so our standard error is going down. Okay, so again here, we know that that green group is taller than the blue group, but there's some uncertainty involved. And that uncertainty is quantified by using a confidence interval. So let's discuss confidence intervals a little bit. The confidence interval is basically a combination of the point estimate and a scaled standard error. So often we multiply the standard error by something close to 2. And because this confidence interval is dependent on the standard error, which we just discussed is dependent on sample size, the confidence interval gets smaller or gets closer together as your sample size increases. Because as your standard error gets smaller, that confidence interval will get tighter. Often in the medical literature, you're going to see 95% confidence intervals reported. And 95% confidence intervals, that basically means if we repeated the experiment many times, then about 95% of the intervals produced will capture the true point estimate. Okay, I'm going to say that one more time because the concept of 95% confidence intervals is pretty tricky and a lot of times misinterpreted. So what it means, a 95% confidence interval means if we repeated the experiment or the study many, many times, then about 95% of the intervals that were produced, if we used the same procedure to produce those intervals, will capture the true point estimate. So returning to our height example, the 95% confidence interval now is 6.2 to 8.7. So this means 6.2 to 8.7 is the range of values that we're 95% confident contains the true point estimate. Okay, so let's go back to that comparative analysis of alcohol control policies in 30 countries. And so before I had said that that point estimate was negative 0.1, which they end up reframing as a decrease in consumption of 1 liter absolute alcohol for every 10-point increase in score. And so they put a 95% confidence interval around this 1 liter absolute alcohol for every 10-point increase in alcohol policy score. And that 95% confidence interval is 0.4 to 1.5. So the uncertainty there around that 1 liter is 0.4 liters to 1.5